Yeah.
Okay, great. So, welcome everybody to the second lecture in the series of data analysis lectures. And Shreya will continue this series. Please take it.
Okay, great. So my goal for today is just to sort of go from the expression that we derived last time for the for the answer-any entropy in any quantum many-body system at late times, and go from that to a derivation of replica wormholes in this PSSY model. So let me first just, and then after that, in the second half of today's lecture, I'm hoping to start talking about non-isometric codes. Okay, so let me just write down the expression that we derived last time again. So the answer-any entropy for this was trace through A to the n at late times. We said that it was a sum over permutations in Sn of this object. Where all these states were on 2n copies of the Hilbert space, and they were defined last time. So the features of this expression were that the dependence on the initial state, rho 0, had dropped out. So it depends only on the equilibrium density matrix. But because of the sum over permutations, it turns out to be symmetric under A going to A bar, so it's consistent with unitarity. And so let me just make a few general comments about this expression. So one simple thing you can do is just take rho equilibrium to be the maximum mixed state. And in that case, this just the result for the entropy just becomes exactly the same as if we were to find the entropy for a random pure state in d dimensions. Okay? And so in particular, the tau equal to E term coming from the identity permutation gives a contribution which looks like 1 over dA to the n. And the tau equal to eta term gives a contribution which looks like 1 over dA bar dn. Okay. And in the limit where either A is much bigger than A bar or A bar is much bigger than A, you can essentially ignore all the other terms in the sum, so you just get exactly Page's result. So you find for the answer-any entropy that it's given by the minimum of log dA and log dA bar. Okay.
So, Shreya,
Yeah.
when you write the second line of row A, what is row A? Second line.
Row A is this way. So it's if you find trace over A bar of the time evolved state. This.
Basically, it's not in the relation with the row EQ.
So you recall that, so we said that rho EQ was the equilibrium density matrix that you associate with this initial state and this time evolution period. So in general, it will turn out that the like we saw in this case, in general, the tau equal to E term will just give you trace rho equilibrium A to the power of n. So that gives you a contribution which just looks like the answer-any entropy in the thermal state. But then the tau equal to eta term gives you this thing in the complement.
So it's the sum over permutations that symmetrizes.
Yeah, exactly. Yeah.
And did you just go directly from one to the other? Is there something in the middle? If you start increasing the size of A?
Yeah, if you start increasing the size of A, if you're in a regime where the dimensions of A and A bar are equal to each other, then all of these different permutations will contribute, and then that gives you some transition, which is good.
Correct. How to match this result with PSSY result, where they got that Sn as minimum of log k or e raised to minus s?
Yeah, I'll be talking about that in a lot of detail. But here we're just talking about just a general statement about any system. But the PSSY case will essentially be a specific choice of rho equilibrium for that case. Okay, so
Sorry, I'm a little lost. SN is minimum of that SN stands for what exactly?
for the nth, so
For
for
the nth Rene,
the nth Rene entropy in,
and then taking the n going to 1 limit. Is that right? I mean, this is the law of the dimension of the, it's the n.
yeah, this is true for all n in this limit where either dA,
It's independent of n.
yeah,
I mean,
Oh, yeah.
yeah. It should just be the lower, maximally mixed with the lower dimension. So the nth, wouldn't the power should, I mean, it's probability.
Yeah, sorry.
Sorry to be so, for the von Neumann, I think this is correct.
no, sorry, yeah. So also I should have written n minus 1 here. But then when you find the nth Rene entropy, you find minus log, minus 1 over n minus 1.
Maybe I'm being dumb, sorry.
Huh?
No, go ahead.
No, so it's just, it cancel, the n minus 1 cancels out.
You take the log.
Sorry, I'm being very haphazard, but,
I mean, Rene is trace rho to the n, right? And rho
Yeah.
would have been 1 over the lower dimension to the, I mean, equal probability is 1 over d to that n, right? And then you would have traced, you would have got n, so why isn't there a,
That's what you're.
I mean, this is true for von Neumann, but not for Rene, right? There's an n. Sn is the Rene entropy, trace rho to the n.
no, the Rene entropy is minus 1 over n minus 1 times the log of trace rho.
Oh, you define it as law of the, okay. That's what I was saying.
Yeah.
Okay, fine.
So then this, so then,
Normally I think of it as trace rho. Okay, yes.
yeah. But
Sorry.
but the thing that you should analytically continue to get the von Neumann entropy is this minus 1 over n minus 1 log of this. So that's why you have this and
Okay.
yeah. So I guess you can also do a more systematic version where you keep all the permutations and then analytically continue that expression. And from that you also get Page's correction to this. So you get this minus the m over n term, like the minus dA over dA bar term. Anyway, so this is the general structure that for general choices of row equilibrium, you find in this regime where one of the systems is much smaller than the other. Yeah.
So, is this equation that it's an n
This one? This is an approximation. So this was the result of the last lecture. What?
is the linear?
Yeah, this is for late times and large Hilbert space dimension.
So, you have to, I mean, it depends on the equilibrium. So, indirectly it depends on the relations.
Yes, in that sense.
So, equilibrium is appropriate.
Yeah, and that is consistent with the general idea of thermalization, that you forget most details of the initial state, except some things like its energy or its chemical potential and things like this. And then,
And if the dimension of it, so suppose I was in a spatial system, and I choose the fraction of the length to be x.
okay.
So then dA would roughly be
Yeah, so then dA would be like e to the x, or e to the xv, I guess.
e to the power x. So now if I took this log, I would get
Something proportional to the volume.
but just additively, right?
Yeah.
So the volume dependence would sort of come out as a function of fraction. It's just a smooth. I'm trying to understand the analytic structure of this as a function of function of x.
Yeah.
Is it right that the volume part is just coming as an additive constant?
So I think this would become something like.
Can you just repeat the question again, Shiraz? You have a line, you have a,
Let's say I've got a space of volume v, and a is of a fraction
of that.
x. So I'm trying to understand this as a function, the analytic structure of this kind of sum as a function of v and x.
So roughly you're saying d will scale like x, some fraction.
So I guess the volume comes out as an overall constant, and then
Log
you
of
have
x plus 1 minus x.
Right.
Which you maximize when x is half.
Right. So great. So there's a v overall outside, thank you.
Yeah.
And then that whole sum, which is and that's a nice analytic. I mean, that's a smooth function of x. Then all terms are sort of comparable.
So not this is not. This is not. In fact, like whenever you're in the thermodynamic limit, you're essentially always in a regime where either a is much smaller than a bar or a bar is much smaller than a, because the dimensions just look exponential. So the things you're comparing are these terms, and then other terms which would look like.
Sorry, schematically, if I wrote out the whole sum,
Yeah.
it would be like v overall outside, and then each term in the sum is some function of x.
If I wrote out the whole, it would be like. Let me try writing it. So we have. So it's a sum of things which are all exponential in the volume.
Good.
And then if you take the volume to be large, then only one of these would be the delay contribution.
Yes, and I'm supposed to take the log before or after the sum in place.
I should take the log after. So the approximation is for e to the minus n minus 1s, right? So I should first find what this quantity is by selecting the delay contribution here, and then take the log.
I see. Thank you.
Yeah.
So I'm sorry, but one thing I asked before again. So then it's just really minimizing this expression, right? Or maximizing this, whichever term in the sum is maximum, we keep that.
Yeah.
And in between, if I keep increasing x, do I directly go from this guy to that guy, or is there something else in the middle?
If you're in the thermodynamic limit, then you directly go from here to here.
Right. So it's like phase transition
Yeah, it's like a phase transition in the thermodynamic.
at exactly half of system space.
Yeah, exactly. Because all of these terms situate only at exactly half of the system.
Okay.
Yeah. This is the answer one you get for R random statement.
Yeah, this is exactly the same as what you get for high random states. And then now, in principle, you have a generalization for if you take this to be the canonical ensemble or the microcanonical ensemble.
Not just the identity, but
Yeah. But the identity case is familiar, so it's useful to see what happens in that case. Okay, so so essentially from this more general expression, you get the expected generalization of Page's result that the nth Renyi entropy is given by the minimum of the nth Renyi entropy of A in rho equilibrium and the nth Renyi entropy of A bar. Okay, so now let's try to understand the structure of these individual terms a little bit more. And in particular, we'll see that you can interpret each of these terms as a Euclidean path integral on n copies of the system. So this is So we can consider this for the case where you take rho equilibrium to be e to the minus beta h over z. And let's just consider the second Renyi entropy for this case. So this will have just two terms coming from tau equal to e, which will be the identity commutation, and tau equal to eta, which for this case will be the swap commutation. So the tau equal to e term, if I just write this out explicitly, will look like this. So now this is just Euclidean path integral on 2 copies of the system, where in each copy I'm going from tau equal to 0 to tau equal to theta, and then I identify the initial and final conditions in a different way on the 2 copies. So, yeah, sorry. In this picture, this is A, this is A bar. Then in A bar, I just identify the copies in this way. And in A, I identify the copies like this. Okay? And then if I looked at the tau equal to eta term, I would essentially just end up swapping the rows of A and A bar in this expression. And I would find that instead of this path integral, which is essentially the path integral for computing the entanglement entropy of this state in A, I just get the opposite of this. So I do this identification in A bar and this identification in A. Okay.
Sorry, this kind of phase transition is exactly what we get in holography. We have a circle and we're trying to compute the entanglement entropy. The thing will either close up this way or that way.
Yeah, you mean even just an empty yes?
Yeah.
Yeah, but I guess the interpretation of that is a bit different because it doesn't have to do with normalization.
Nice. Yes, thank you.
I mean, the first way of pairing up is what we will normally call trace square, right?
Yeah, if the row that you were interested in was this,
Yeah.
but because the actual row that you're interested in is this time evolved state of a pure state, you also have to include this other geometry, like this other.
Okay, so and you're doing this starting with what state, or it didn't matter?
It was just some initial pure state which resembles this row equilibrium.
Okay. Oh, sorry, initial pure state which? I mean, what was the row equilibrium there?
So row equilibrium was just taken to be the equilibrium density matrix such that if you look at things like expectation values of free body observables, then those are the same between psi at great times and row equilibrium.
Sorry, what I'm not understanding is, had the state you had started with being row equilibrium, only one of those diagrams would have contributed, the first one, which we normally write.
Yeah.
And here you are saying you start with a particular state which is not row equilibrium, and you add those other diagrams, you add the other diagram.
And it's a pure state. You're starting with a pure state initially.
And then it doesn't matter what that pure state is. You'll get that other diagram.
As long as the pure state is something which should be associated with row equilibrium.
And that's the part which I'm not. What exactly does that mean? Should be associated with something?
Yeah, I think it's so like we were discussing last time.
Some things are thrown away in that diagram. That's what you mean. Yeah?
Its energy is that of the
Yeah, sure, yeah.
Energy. Oh, that was the point. Okay. Energy is the same. As long as that's the case, then you get another diagram. Okay,
Yeah. So somehow, but the expression that we started with was Lorentzian path integral on 2n copies of the system. But then we did a series of approximations, and finally we ended up with this expression, which is a sum over Sn Euclidean path integrals with some unconventional boundary conditions.
Okay. And the other diagram is this one that you have here.
Yeah, this is the other diagram for S2. But if I were calculating Sn, then I would get many more diagrams associated with all the different.
And here the A is identified in one copy itself, and the A bars are identified across.
Yeah. Yeah.
Is there a way to say what this answer is in terms of random states? For row, I mean, not for just identity row EQ, but general row EQ.
But for what?
General row EQ.
For general row, is there some way to formulate it as an average over some random
Some
state?
random state which has some row EQ included.
Yeah, I think that there are a few ways to.
Is
Yeah.
it just U, row EQ, U dagger, randomized over you. If I take that state, do I get this answer?
Um, sorry, say it again. So,
Maybe this is wrong. Maybe I just one example. Candidate.
OEQ is not a pure state.
Yeah, that's why it do not have this property.
yeah.
Yeah, it do not have this A symmetric property. But randomizing means
Yeah, I think that there are some other ways of getting similar results from averages. So, for instance, you can do something called, so there's another paper, I think I mentioned a paper last time by Grover and Liu called Renyi entropes of chaotic eigenstates. And they have something in that called the ergodic bipartition ansatz. But basically, it's like if you take, I think you can, like, to get this answer for the microcanonical ensemble, you can just take essentially some random state in a narrow energy band.
yeah, that is just like rho EQ behind identity, right?
Yeah.
But I'm saying so general rho EQ, is there a way to, or maybe that's a
For an
canonical ensemble,
arbitrary row equilibrium.
or canonical ensemble, maybe that.
Yeah, for canonical ensemble, I think there are some things called canonical thermal pure states. And they formulate some average, like some e to the minus beta h acting on a random state. I don't remember it exactly.
Is
But
it like maybe a thermophilia double state randomized?
it's not a thermophile double because it's just on a single copy. But somehow they weight like the original random states with some factor of e to the minus beta h. So yeah.
Yes, that's why I'm not listening.
Where rho EQ, but is that identity? I think that is just the standard tails. It reduces
The
the
microcanonical ensemble.
Yeah. Oh, I see. So they have a canonical.
Yeah, they have the analog of that state that share.
Okay. Canonical.
Yeah.
I ask this because, thinking about it that way may give some physical idea as to what that state is effectively. In some sense, in what sense is it some random state,
On the
but has imprint of EQ?
yeah.
That's what I was.
Yeah, I guess it would explain a little bit more about what the structure of this pure state is in the Hilbert space. Yeah, but I guess the nicer thing about this perspective is that you can derive this from the time evolution in some sense, and you don't have to rely on the random average in the Hilbert space. But yeah, I think that you get.
But maybe the time evolution is doing that.
Yeah, somehow the time evolution is turning the original state into a state which looks like this. So at least I think at the level of these Renyi entropies, you can match results from averages like this and this expression. But I'm not sure if it would match in every respect. So maybe there's some other quantity you can compute between the two states which would not be the same. Yeah, but it gives the same result for the Renyi entropies.
And just to get my the basic sanity checks in place, if the dimension of A bar had been much bigger than A, the second diagram wouldn't have gone. I mean, then
The dimension of A bar, yeah.
and that just somehow you can see manifestly, is it?
You can see it from the result.
Those sort of things.
Yeah. Just by seeing that in that case, the contribution of this diagram would be much smaller than what. Yeah. Yeah. Yeah.
So this beta LS by del E evaluated at the
Yeah, it should just be. Sorry.
beta the del S del E, whereas the entropy the energy that we have was
He's asking if the data can be obtained by ensemble equivalence between canonical ensemble and microcanonical ensemble. Whether this beta is the same.
It should be the same. Yeah. Yeah.
So this rho equilibrium which one can for any Renyi entropy.
Sorry.
Can we fix rho equilibrium for any Renyi entropy? Is it independent? Because the consistency condition satisfy this for all.
Yeah. So I think you should use the same rho equilibrium for all the n's.
But
Is the consistency satisfying?
So you only have a self-consistency condition for n equal to 1. Because that's the special case in which this trace of A bar rho just becomes trace of rho, which has to be 1. But there's no analogous condition for the second domain. I think there's some sound from Zoom. Yeah, it's okay. Okay, yeah, cool. Any other questions?
So
Okay.
this is commenting the last case about the other permutations going to zero in the thermodynamic limit. How do you see that? Like you said that all of those terms are proportional to volume, right?
All of these terms are exponential in volume.
Including the other permutations besides the E and the eta term.
Yeah, because everything, like all the different terms look like dA to the some power, dA bar to some power, over d to the n.
Yeah, so I didn't understand why those terms would go to zero in the thermodynamic limit.
Yeah, because in the thermodynamic limit, you're always in a situation, so these will end up looking something like dA to the minus k1, dA bar to the minus k2, where k1 plus k2 is equal to n minus 1. And then you're comparing these terms to 1 over, sorry, I should have space. So, this first term would look like e to the minus VA and minus 1. And these ones look like e to the minus k VA to minus k VA bar. So if we're in a regime where VA is bigger than or is smaller than VA bar. Okay, so let me check. So if VA is
No, but that's also the limit x is small, right? But I first take the limit v goes to infinity before I take the limit x is small. Right, for the thermodynamic.
yeah, so okay.
So will this keep all of them?
It's e to the power of v times f of x, and then sum. So the biggest one wins always.
Yeah, it's just everything else except for if
Okay.
if x is less than 1/2, then one of these will be, all of the others will be exponentially smaller than this.
It's like a sum over saddle points.
Okay.
The leading saddle point always dominates.
So essentially, yeah. So the reason that I emphasize this point about how you get a sum over Euclidean path integrals with some unconventional boundary conditions is that this will eventually give rise to the unconventional geometries of replica wormholes in PSSY. But seeing it this way shows that this is a general feature of any quantum many-body system. Okay, so
Yeah, and the problems with the in two-dimensional conformal field theory, if you're computing the Z, then that would correspond to having like a geometry with two cuts which are viewed.
wait, so you mean in the thermal state?
Yeah, just
Yeah.
I would say. And then so that would correspond to some 4-point function of twist operators.
Mhm.
So that corresponds to a certain function of the cross ratio.
Mhm.
Now, in the limit of infinite central charge, there's a formula by Zamolodchikov which shows a phase transition when the cross ratio is less than half or greater than half.
Okay.
And that is basically your phase transition here, an exchange between A and A, just a comment. For a finite central charge, there is just one answer.
Okay.
There is no, but the function of the cross ratio shows a discontinuity when this cross ratio is less than half or greater than half.
Yeah, but I'm not entirely sure if it would be the same thing because somehow here we're looking at not the, like, if the calculation that you said is for the thermal state, then it seems like it's not quite the same state that we're looking at here.
Oh, sorry, excuse me. No. It doesn't have to be thermal state. It can
Okay.
be in those pure states of characteristic Carnot.
Okay.
Sorry, yes, indeed.
No, but even in that case, Gautam, I mean, this is about some over permutation structure here is absent there, right? Because that's just fixed state that you work in, and you do insert the fixed twist operators that are required by the that are required to produce the NE proteins. Yes. And then I think the phase transition is really, I'm not sure whether it's of that kind.
Yeah. Also, in this case, I'm not
It's an
sure.
exchange between A and A bar there also. So I'm just, maybe it's not the same.
No, but it should be similar, but one cut on a circle instead of two cuts. I mean, if you have what she's doing is like one cut here. And when the cut becomes larger than the size of the circle, it goes to the other guy. You've got one cut here, and then her formula tells you that either you're computing the entanglement entropy of this guy in thermal equilibrium, or of the other part of it in thermal equilibrium.
So your calculation is the pure state.
It's in a pure state that will eventually go to that resembles a
But
ray.
if you just have the structure of two mark points on the boundary, there will not be any change. I mean, the anchoring points will always be the same.
Anchoring point, but you can either close up on this side or on that side. You take the 2 points.
The cut.
Yeah, there are two twist operators.
Yeah.
And there's one OP limit here and another OP limit there.
Yeah. I don't think this is structured.
So in this case, what happens is that the kind of states they're talking about in the bulk when you have end of the world range. So, the RT surface can either close up on itself or it can go at the end of the world range.
So this is some boundary
I thought it was
conformity.
just the vanilla pure state in some CFT. CFT vacuum.
Conformity theory in a circle.
Okay.
You have to put in the information that you have this state, this
Okay.
heavy, this heavy energy state.
Okay.
So it might eventually be a 4-point function, because you're doing it in some state. And then you do this. It should, certainly from ADS-CFT, it should close up. I think in that state, I think we're going.
Okay. Yeah, that sounds really interesting. Maybe we can talk about it later.
Sorry, I don't understand. This is the vacuum state.
Not like
Not
it's a very heavy state.
very heavy.
It's a pure state with a lot of energy. So it's some sort of 4-point function.
Yeah, then yes. But yeah.
I see, but you can somehow explicitly do calculations in such a state in a CFT.
I would do it by putting heavy operators.
I see. Okay. But some arbitrary heavy operator.
Some arbitrary heavy operator,
Okay.
put 2 operators,
I see.
and then look at this.
Uh-huh.
And I think you should see your transition.
Another way to see that is, more in line with what you're saying is to have these Kronecker Lagrangian states, which are boundary CFT states.
Mm-hmm.
These correspond to having end of the world range.
Okay.
Roughly speaking. Then there's a different kind of phase transition, but RT surface can go ahead and give.
Yeah, like in Hartmann-Wallach.
Yeah.
Okay. Yeah, that might be different ways of seeing this kind of transition.
Basically, because you start with the pure state, you have to treat A and A bar symmetrically. I mean, that's the basic outcome diagrammatically,
Yeah.
right? You do the contractions in a
Yeah,
symmetric way,
exactly.
and then whichever one is the larger dimension sort of ends up
Yeah.
dominating. Zero count. Yeah.
Yeah.
Which makes sense.
Yeah, it doesn't, yeah, exactly. So this was just trying to drive it a bit more systematically, but it's
which is very important. I'm just saying it. Yeah.
Yeah, but yeah, the essential idea is just somehow you should treat the ANA bar symmetrically, and this is how you
Yeah.
And there's a parameter which is this large system size,
Yeah.
which makes the formula very simple.
Yeah, exactly. Okay, so let me quickly try to review the PSSY description. I guess more generally, I should say that if we assume that we have some unitary quantum theory of gravity, then in principle we could just apply this prescription to the Euclidean path integrals of that theory. But we don't know how to formulate the Euclidean path integrals of a full quantum theory of gravity. So instead, we're going to use holography, and we're going to essentially treat these things as boundary partition functions in our holographic theory, and then the logic would be to then equate the boundary partition functions with bulk Euclidean path integrals, and this will give a derivation of graphical elements. So the explicit example where we will try to match the results from doing this procedure and the results from existing prescriptions is in the PSSY model. Okay, so in PSSY, they have a model of a black hole in 1+1 dimensions. With end of the world rings behind the horizon.
Since it's come up, sorry, Onkar, I know this is a pet peeve and I want to slow down. I mean, what's the rigorous derivation of the end of the world ring in JT gravity, just once and for all? Because if I quantize that theory properly, I don't see any end of the world rings. Sorry, I really can quantize the theory, and there's no end of the world brain. You can't cook up boundary conditions randomly in a theory of gravity. What's this object? I mean, I give you the action, I can quantize this theory. You give me canonical, I do a canonical. You give me path integral, I don't see any end of the world. Sorry, just once, then we'll go on. I don't know how people just cook these things up. It's a consistent theory.
Yeah, I don't know either, actually. This is one of the things that makes me.
You can't just do this.
Onkar always quotes this appendix.
Yeah, so what the appendix? Just once quote it again because I really have to study this.
I mean, the way they show it in the appendix D of their paper
Yes.
is that you consider random superpositions of energy eigenstates and put these Boltzmann factors that Shreya was putting in. Right? And then you try to compute overlaps of these states using standard rules of JT gravity.
Okay.
Basically, what you do is because this is a random superposition, you first do the average over the coefficients of the random superposition. And then it turns out that the calculation now boils down to a calculation in JT gravity with some objects, some particular specific boundary conditions, which can be identified as end of the world.
So the starting point was a matrix model?
Yeah.
And
But was your question more just from the gravity side? Why is it justified to include such objects?
Yeah. I mean, because, okay, now maybe the gravity quantizations I have in mind is the standard sort of, quantum gravity quantization, and it's not including boundary conditions where the boundary theory is in a random superposition. Maybe that's the assumption. Okay. I really have to get this out of my system.
Yeah. I guess people say vague words about like doing some kind of orbifolding, like the original geometry, and then you get an end of the world ring. I don't know what you mean.
It's well defined with the usual boundary conditions on the boundary of any space. Okay, anyway, go ahead, please. Sorry.
Yeah, no, this is a good point because I don't understand the physics of the end of the world brains either. And for us, the physics of the end of the world brains will not actually be very important for this replicable wormhole stuff.
I mean, more generally, so what's the take home? Like in string theory, deep brains are not just random objects. They're very specific objects. You can just put them up in string theory as well in the context of ADS space, depending on random superpositions. Is it a property of 2D JT gravity? Okay, never mind. Okay, all right, please go ahead. Excuse me.
Yeah. So I'm just going to try to explain what I understand about this model. So there are some end of the world brains behind the horizon, and so the Lorentzian geometry. So the orange line indicates the end of the world brain. So that's some geometry like this. And the end of the world brains come with some number of labels. So they're labeled with I going from 1 to n. Okay, and the radiation in this model is just some quantum mechanical system which is not shown on this diagram, but it has some n orthonormal states, which are also labeled by I. Okay. And then there's a Euclidean version of this geometry, where you have some disk which is cut off by and then
Sorry, but just about Sandeep's question. Maybe the general claim would be that suppose I take one of these high energy states, even in n equals 4. You specify that the white guy is like the boundary theory, right?
Yeah.
The white guy is the boundary, and the orange is the end of the world, right, Shreya?
yeah, that's right.
So suppose you were doing a partition function, which is a transition amplitude between one state and another, and your state was extremely complicated. It was one of these states at energy n squared, and you were trying to find the bulk dual of this computation. Because this is like one of these n square type states, it's hard to know how to put that information in the gravity. And maybe the idea is that always something funny will happen in the geometry, completing the end. Does that sound reasonable?
But I mean, okay.
I mean, I'm not saying the particular nature of this funny thing is reasonable, but that something will happen along roughly like this Takayanagi idea. That you do something funny on the boundary, or something funny will happen, more or less.
The fact that it's so local.
Yeah, that's crazy.
So,
I mean, the fact
That's crazy. It will be some fun.
Well, I mean, yeah, what's funny should be within the rules. I mean, maybe you get a singularity, maybe you get a black hole. That's fine, you know. What's this sudden object? What are the rules for strings here? Dirichlet, Neumann, what? I mean, any tension? Okay, never mind. Sorry.
Yeah.
Okay, but I fine. Yeah.
Okay, and then they have a model for what happens during the evaporation process. So during evaporation, we have some state psi in the combined Hilbert space of the black hole and the radiation. And this has a structure like psi is equal to n. So this is an assumption that the state looks like this, where this psi I is a state of this system which has an end of the world brane, which is labeled by the index I, the same index I. Okay.
So, I mean, just to correct, this clearly means that some state of the internal system label being denoted with this. Some excited state, right?
Yeah. In a way, that's an element of the dictionary we don't really know. Right? If I want to find, there's a field theory path between one state and another. And you can ask where is the bulk dual of that? That's some element of the dictionary we don't, I think, at least I don't know.
I think, why can't you, anyway, generate that state by turning on operators, each of which has a bulk dual, and you say, well, it's an n square thing, but I have many gravitons that fire.
But the gravitons give you high.
Okay, yeah.
Highly overcomplete at this stage. It's these gluon states that you want to have. And we don't really know the gravity, actually. Sort of one of the states of a black hole.
Okay, well, let me ask you, I'm not sure we can't do it.
Okay.
We're just throwing bunches of graviton.
And waiting for them to throw that.
so this relativistic integration
And you
of
form
these
black holes,
states.
you never get the same.
The number of states you can make by gravitons is parametrically smaller than the number of states in a black hole. Because the number of states in a gas of gravitons at energy order n square is parametrically smaller than the number of states in a black hole. So you can never get it. Yes.
Why I can't throw in enough gravity? I see. You say when it forms a black hole, that won't count correctly then.
You will only form very particular states. Because just count the entropy of gravitons at energy n squared. That's exponential of e to the power, I think, 18 by 20 or something like that. I mean, less than the number of states. So that the number of ways you can make this is smaller than the number of states. You can never get out of it.
Okay.
Collision. Like, I mean, one can make these brains low energy states.
That's what he said.
I'm saying you can never
That's
make the
what he
generic.
said. You're saying you can't make
You
it.
can never make the generic. Let's count the number of states at energy E that you can make using gas turbines. Okay, the number of states in an energy E is like e to the power 9 by 10. E is n square, so that's e to the n to the power 18 by 10.
I'm not necessarily saying generic state.
No, but that's what I'm saying. Saying that this guy here you should think of as a complicated generic state.
No, what I'm saying is that in ESFY model, if you just follow the derivation, then this state could as well have been a random superposition of low energy states. So I'm not sure the relevance of this. It doesn't require high energy states.
It's in two-dimensional, actually.
So that's the gap in the ADS CFT dictionary that this is bringing out.
This dimension,
It's almost more important than the everything they've done. Anyway, okay.
Yeah, sorry.
Sorry, Shreya, go on. Yeah. It's very interesting. Very interesting.
Right. Yeah, sorry, so you were trying to figure out some way to form this, like,
Yeah, but go on. We accept that this is an end of the world train. Yeah.
Okay. Yeah, I mean, there are many confusing things about this, which is part of what I wanted to emphasize. Okay, so if we look at the reduced density matrix, so assuming that this is a state, then if you look at the reduced density matrix and some matrix element of it on the radiation, then this will just, using this expression, be given by the overlap of psi I, psi j. And then they give a prescription for calculating what this object is. So they say that you should calculate this. Okay, that's also in my last sentence. Okay, so for calculating this, they give a prescription, which is that you should start with some boundary condition. So they want to calculate this using the Euclidean path table. We say the boundary condition is that you have some indices I and j, labeling some endpoints, and then you have an asymptotic boundary in ADS2. And then they say that you should fill in this boundary condition with all possible geometries. And when you do this, then you get an end of the world brane connecting these two endpoints. And because of that, that comes with a factor of delta ij, because you also have to connect these indices. And then you should just fill this in with the bulk geometry to get some Euclidean path integral on one copy of the system. So I'll call such a Euclidean path integral C1b. So the whole thing is C1b times delta ij. Okay. And then they say that if you have...
Very sorry, so this diagram, I and J denote states of the radiation, presumably.
Yeah, and also this internal state at the end of the world brane. So when you connect these with an end of the world brane, then they say you should get a factor of delta ij.
So these are orthogonal in that sense, I guess, the psi I B's.
In this sense, if you look at this quantity, then we...
These intersections and that intersection are same, right?
Which intersections?
And that intersection are
This
that
one.
one. Yeah.
Yeah, I should just have labeled it with one line because I have to do. Yeah.
Sorry, B was the braid. Psi is equal to B cross R. What?
B is the black hole jump, like the black hole part of this diagram. So B is this whole thing.
And R is something outside this radiation.
Yeah, R is the radiation, which is just treated as some quantum mechanical system which is outside this.
Okay.
And so, yeah, so they're saying that, this looks like some analog of Hawking's state if you have an entangled state like this.
Yeah, and I should think of B as essentially living on the end of the well. The psi I's as living on the end of the well brain.
Yeah, somehow the only thing that should be different between the different psi-IBs is the flavor at the end of the word.
Okay.
Yeah, so one point that confuses me about even the statement at this level is exactly why you should be using such a Euclidean pattern to give this matrix element of rho r. I don't really understand how this comes from the actual evolution of the system.
Just explain the path integral again once. What exactly does that diagram mean in path integral terms?
So the diagram means that you have some, you choose some temperature beta,
Okay.
and then this is an asymptotic boundary in JT gravity of length beta,
Okay.
and then you integrate over all possible geometries in JT gravity, which look like this.
If you look there, they have an end of the world brain and they have the boundary
Yeah.
of length there.
Yeah.
And what about the I and J sticking, those dashes? What do you do?
So the I and J's just give you this factor.
Okay. That just means you're doing JT gravity with a end of the world brain, presumably of I type. Is that what that means?
Yeah, exactly.
Oh, should I think of this as computing a transition amplitude between the ith and jth state on the boundary? And then that sort of gets filled in by the end of the web. I mean, we should be doing some sort of boundary calculation.
Yeah, I think you can think of these you can think of these as labeling the boundary versions of this geometry.
Yeah. I was thinking we get some states on the boundary theory, whatever it is, and computing that. And they're giving you an ADS-CFT rule for how to do it.
Yeah.
The ADS-CFT rule is that you fill in the geometry with this end of the well brain, and the I and J label sort of runs without drama on the.
Yeah, but that's what I'm trying to figure out. This is JT gravity, not to slow you down, this is JT gravity with n massless scalar fields, let's say, right? And I know the rules to do all Euclidean calculations if you give me the usual boundary conditions for the scalar fields and for gravity, right? So what? And I don't see, anyway, there's no end of the world. I mean, you do the path integral, okay? It's a very well-defined path integral.
But there's also no I and J in that.
Yeah.
Set
So what I'm
the
going...
microscopic theory has lots of states.
No, but they are all specified in JT gravity with matter in manners we know, as per the standard rules of JT gravity.
And let's say we're trying to do I should shut up, but let's say we're trying to do SYK, and there's not even massless matter. Still, the SYK ground state has a lot of states. And wait, those I and J, I think of as labeling those states. Correct.
Yeah, no, I
But JT gravity is anyway. I mean, there's no analog in JT gravity except S0, the topological counting parameter, which is a parameter in the theory. Okay, that's it. And then there's the rules of Euclidean gravity. I mean, I have gravity, I have massless scalar fields. I put non-normalizable boundary conditions, whatever. I do the
in that setup, one always computes partition boundaries. So in other words, the boundaries that one considers are always circles, which are to be part of this partition boundaries.
No, not at all. I compute arbitrary correlation function.
No,
Anything I can compute in ADS-CFT,
But not with pure states, that's what.
Yeah, I was trying to say that you
No,
don't
not
have
pure states. Because I can create a pure state out of vacuum. In ADS-CFT, we can compute pure state correlation.
Maybe this.
Am I missing something?
Yeah,
Sure.
things like the DSL states and so on.
Yeah,
They are probably beyond the gravity thing. Maybe it doesn't have a gravity interpretation. Maybe that's what.
Sure, but the claim is that if you consider sufficiently random superpositions of these I or D states, which you might think that they don't have any gravity interpretation, then they do in terms of this actual thing.
No, so it's not a statement anyway to come back. I understand in JT gravity, that's all I'm saying. Root GR plus phi, quantize it with n massless scalar fields. But what is the boundary condition you would like to add? I don't know that. If you say I'm going to ad hocly put a end of the world plane, okay, then fine.
But gravity doesn't see the microstates of the black hole.
Yeah.
And here you're trying to do.
So then you're saying I'm not doing a calculation in JT gravity.
Right.
You know, I'm doing it in SYK. That's a different statement.
Yeah, but this is what Munkasi is saying, that there is some modification of the rules of JT gravity that allows you to compute some random whatever, something.
Yeah, I mean,
You are trying to not solve the information puzzle in SYK. We know the answer. There is no puzzle. You're trying to solve it in gravity, and you're giving me a gravity theory which is ill-formulated. You know, I'm sorry, but no, that's, I mean, give me, I know JT gravity is well formulated. And if you say in that theory, is there or is there not an information puzzle? Fine, I accept the question. If you say I have some ill-formulated theory of gravity and I'm asking, I'm sorry, formulate it for me. Okay, never mind. That's all I'm coming to. Okay, go ahead, Shreya. I apologize. All I'm saying is I don't know how to go Shreya is saying in terms of the boundary conditions, in terms of data on the boundary of data.
No, even I don't know how to do that. So Omkar knows it.
No, it's not like, if you just write down what the psi I is, right, in terms of the microstates and the matrix model, the energy eigenstates of the matrix.
No, but the matrix model is not JT gravity. JT gravity is integral root G bracket R minus phi.
Yeah, but you're doing a calculation in the matrix model.
I'm translating it to gravity.
So you're saying that
Is
on
the information puzzle being raised in matrix model or is it being raised in JT gravity? Hawking's question was about gravity, so the question has to be raised in gravity.
Yeah.
So what is the precise theory of gravity in which you want to raise the information puzzle?
It's JT, it's this quantum system that's doing the JT. The puzzle.
No, then it's JT gravity, right? The gravitational system is, give me an action. Please give me an action, right? I mean, how do I know what is the theory? Please give me an action at least. I'll tell you whether I can do the path integral. The only action I know of is phi r minus. Okay, there's something else, give it to me and then we'll pose the question. I'm just saying it's ill-posed if you say it's matrix model, something like that. Then it's a matrix model question. Then I know the answer. Okay, anyway, all right, maybe we can make
I
it
think
more
maybe our
precise.
first point is like, I actually don't know this appendix well, but like you say that they have some boundary expression for this state psi,
The psi ions.
for these psi i's.
So these are excited states of the SYK theory at low energies, which account for the entropy S naught.
They're not at low energy.
Presumably it's low energies, right, to get to JT gravity. I mean, you can I thought it's the E to the S naught. Yes,
Yeah, it's the states that make up the line. Yeah, give you the
yeah, and the thing is, JT gravity gets the S naught, but it gets it in a very dumb way. It gets it as the topological counting parameter.
No, but you want to, yeah. But you wouldn't be able to insert any one of these states in JT gravity, right?
No, I agree, but then you need, see, if you take JT gravity as the S wave approximation, it doesn't see it either. You need strength here in Ashok Sen to do the calculation. No, really. So what you're led to is pose the question, if you want to answer it, just to go back where we started, pose it in string theory, you know. Otherwise, you can't answer the question because you've not accounted for S now. I mean, okay, never mind. Okay, anyway, all right. Go ahead, sorry.
Yeah, but just to say again, so this is apparently the rule for calculating this matrix element, but as we can see from this discussion, we don't really know where this rule comes from. So that's one of the confusing things. And then they say that now suppose that instead of a single matrix element, you wanted to calculate some n-trendy entropy of rho r. So so suppose you wanted to calculate trace of rho r cubed, which I can just write in terms of these matrix elements. As a sum like this. Then they say, okay, take the boundary condition for one of these rho r's, for each of these rho r's. So you get some boundary condition, which looks like 3 boundaries, and then they have some indices which get connected because of this matrix product. So then you have a picture like this. Okay, and then now they say that you should fill in this boundary condition with all possible geometries. So, the obvious one from that picture is this geometry. And then this will end up having one loop of these indices, which will give you one factor of n. And it will have three factors of this partition function.
Yeah, sorry, just to make sure the dotted, okay, the solid line is some index and dotted is some. Solid is
Solid is not an index. So solid is the end of the
boundary, it's just the end, oh, it's the end of the world.
Sorry, part of it. These should have been orange.
So
So the
those are the end of the world brains, and in a sense, the dotted are the radiation indices.
Yeah, exactly.
Okay, thank you.
So then this gives some contribution which looks like n times z1.
And sorry, this is because the state was II. Let's say transferring radiation index into this field theory state index.
Yeah, exactly. Okay, so that's the obvious geometry that you should fill in with, but this would seem to give, there's also some overall normalization factor, but this seems to say that the entropy of the radiation, so there'll be some overall normalization that you get in this calculation, which would be like 1 over z1b cubed, 1 over n cubed. So eventually it would seem like the answer you get for the second Renyi entropy is always that the entropy of the radiation is given by n and it keeps growing, and you get the information paradox.
Sorry, just the n counting here is z. Can you just go over that? What
Yeah.
are these n factors?
So this is some factor which comes from the overall normalization.
Yeah, just trace rho, right?
Yeah.
Trace rho q. Is that right? Trace rho r q. Is that right? I'm just asking. We are writing the expression for the trace rho r q. Right?
Yes, yeah.
And I was thinking you want to normalize your rho r, so that is that denominator.
Yeah.
Okay.
So that should also have been there in this picture.
Yeah.
But the non-trivial thing is this factor, which you get from this one loop of n's.
One loop of radiation.
Yeah, and then you get three factors of ZD. So if this were the answer, then you would conclude that S3 of the radiation is always just given by log n. And in particular, if you model the process as n keeps growing with time, then this would give you an analog of the information paradox. Okay, but they say that instead of just including this geometry, you should also include in this picture other topologies.
So if I understand, I'm just simplistically, you're allowing for an arbitrarily large number of end-of-the-world brains.
Yeah.
And each Hawking quantum that comes out is correlated with some brain, so n quanta come out.
Yeah.
You're getting that, right?
Yeah, exactly.
Basically.
Yeah, and this was supposed to be like a model for
The
the actual evaporation process, in some sense.
got it.
But then at some point, this log of n becomes much bigger than black hole entropy. So,
Correct. Okay.
okay. So the new prescription is that you should also consider topology like this one. And then now this gives you a single factor of the partition function of the black hole and three factors of n. And again, you have some overall normalization. Okay, so now the result for the Renyi entropy that you get from this will be proportional to the black hole entropy in the regime where this dominates. Okay, so the main non-trivial thing was including a geometry like this one.
And here, just to make sure, the end of the world brain indices connect I mean, each of those solid lines is the asymptotic boundary.
Yeah.
And
The white solid lines are the
white.
orange ones are the end of the world.
End of the world.
And the index just flows. Nothing happens at the end.
So then it does seem that the asymptotic boundary conditions have to be specified in terms of indices I and j. No, in some way. It's not just the internal end of it.
I think it's really good to overlap between states in the boundary. And it's how I think.
Yeah, I guess this is what you're doing.
So the white boundary curves remain where they were,
Yeah,
like in the previous diagram that you drew.
yeah,
And the gluing between these brown guys, the end of the world brains
yeah,
is different depending on what you.
yeah, exactly. So in the previous version, all the asymptotic boundaries were disconnected from each other. And now you connect all of them via these end of the world regions.
Yeah, I'd really like to understand some time slicing and stuff that Sheila was saying.
Oh, in field theory.
Yeah.
Maybe previous time.
Yeah.
Yeah, so that sounds good. Okay, so now we would basically like to understand better we would like to give some systematic derivation of this prescription from the equilibrium approximation to explain more, try to give a better explanation of where these things are coming from and why they seem to always just orientate. Okay, so
What happens with the other topologies where only two black holes are attacking?
yeah, those will turn out to, those also contribute, but their contribution is subleading except in the case where the dimensions are similar between the black hole and radiation.
Very similar to your
Yeah,
permutation.
it's the same thing, yeah. So we apply the equilibrium approximation to the boundary version of this system. So we start with some, again, so we imagine that in this setup, we started with some initial state psi, and then at later times, the system got divided into the black hole and the radiation. So these are some boundary versions of the black hole and radiation. And then this final state, psi of t, which is obtained by some unitary evolution from psi 0, lives in V times R. And resembles an equilibrium density matrix, which we say is given by, or let me write the I alpha for this equilibrium density matrix, which is given by the identity on the radiation, tensored with e to the minus beta A on the black hole. Okay, so this is saying that the radiation is just like some finite dimensional quantum mechanical system with no energy constraint. So you can take the maximally mixed state as its equilibrium density matrix. And then the black hole is some system which should be associated with a finite temperature. And yeah, the black hole and the radiation can be at different temperatures because somehow the radiation gets separated from the black hole after it's emitted. So in principle, their temperatures don't have to be the same. Okay, so now with this expression, we can just directly apply the prescription that I mentioned before. So just using the equation that I'd written down before, which was the sum over permutations with some choice by alpha.
But understand, I mean, if you, I won't stop you too much, but I mean, by positing these end of the world brains, they've just turned the gravity system into any other quantum mechanical system. You have n internal states which can entangle with Hawking radiation. Just to ask, I mean, so the puzzle is that you have nice smooth horizon, there doesn't seem to be anything funny. I mean, haven't they done basically this? They just said, look, no, am I wrong? They just said, look, okay, you have, n quanta come out, you have n internal states and we are positing objects which correspond to the internal state.
Mm-hmm. I think, yeah, their goal is maybe not to explain the
Yeah,
consistency with the smooth horizon, etc.,
Okay, okay.
but just to
Give a
give some calculation which can
Okay.
give you a unitary result,
Okay, okay.
and which involves some semi-classical gravity path integrals.
Yeah, as you show in the last figure that disconnected to connected. So is it a time evolution that as the Hawking radiation progress? Because as we see the entropy is sometimes log in and it becomes entropy of black hole, right? From connected from disconnected to connected.
Yeah.
So it happens so it is related to the time evolution of Hawking radiation.
Yeah, I suppose you model the time evolution of the Hawking radiation by saying that n increases with time.
Yeah. So I can say that it's a time evolution that going from disconnected to the connected with all the geometries.
That's what this
Yeah,
switch
you
of-
can see that as a time evolution. But here somehow everything is kind of being put in by hand about the time evolution.
I'm not quite off that comes out just a gravity. I really can't be saying this.
So you posit a number of states equal to the black hole, equal to the topological. I think they're changing JT gravity by saying I don't have the topological counting parameter, but I'm positing so many internal states which are some n.
But they posit in a way, in their crude positing, they posit even more. Because you could have up to n states, perhaps more than the entropy of the black hole. But then gravity will show you that there are no more than the entropy of the black hole. That's a sort of cool thing, right?
So, but then you do
Yeah,
thermodynamics.
by including these four.
Then you do just thermodynamics. I mean, if at energy E you had,
Roughly the internal partners of the Hawking radiation look like orthogonal states, right? So you've got these n states outside, looks like you've got n orthogonal states inside. And they're going to show you that gravity sees that they're not linearly dependent.
the gravity path integral.
Sees that. It's sort of cool.
Okay.
Yes.
Sorry, Shreya, you made some remark about the temperatures and the radiation and the temperature of the black hole
Yeah.
not necessarily being the same.
Mhm.
Just explain what's what
Yeah, so somehow, because the emitted radiation, it can be, like after it's emitted, it's just free and can be separated arbitrarily from the black hole. You can, in principle, you don't have to have the same temperature for both of them. Like they're not constantly re-equilibrating.
But they have achieved equilibrium.
You can treat them as having separate equilibriums somehow. Like they don't have to have the same temperature.
But they're still in contact, or I mean, what?
So somehow the radiation is not in contact with the black hole after it's been emitted.
I see.
Yes. So somehow in order to,
Yeah, I mean, in the you were talking about the boundary calculation, right? Absolute calculation. So you have explicitly switched off the coupling between the two systems, the black hole and the radiation.
yeah, somehow I think the idea is that they interact. This is just a model for the evaporation process. So, so during the evaporation process, the black hole and the radiation interact for some short amount of time. Then the radiation is emitted, and then it doesn't interact with the black hole again.
So there is an interaction part of the Hamiltonian, or not? I mean, the
Yeah, there is.
unless
In
I-
principle, there should be some interaction part, but somehow both of these systems are large, and the interaction is just some local thing which exists for a short amount of time. Then we expect that the contribution of that part
which
is
is
not.
switched on only for a short amount of time, and after that it's switched off. Is that the thing? Or?
Yeah, I think that's it.
I can switch here. Yeah, of course. If I switched off, then they can be in their separate equilibriums.
Yeah. Okay, so if you put in this value of phi alpha into the expression that I wrote before, then you just get the following expression. So you get 1 over n and the sum over tau in Sn. Sorry. So this is just full expression. So in each of these terms, you get some number of powers of n, because n is just exactly like the infinite temperature version. So it gives something similar to the page result. And then for the black hole, because it's at some finite temperature, you get this product of partition functions at different temperatures.
N is the number of quanta or whatever in radiation, right? N was what?
N is the Hilbert space dimension of the radiation. Okay, and each of these Z and V's is trace of e to the minus and theta e2. So each of these is of order e to the s0 times some order 1 thing, which depends on.
Sorry, I was spacing out. What is now? You're now trying to connect their models. Your way of thinking.
Yeah. So I'm just making. So yeah, I'm temporarily forgetting about their model.
Yes.
And saying that in our approach, we just consider the boundary dual of the evaporation process.
Yes.
In this process, we started with some initial pure state to
Yes.
start. Then the system underwent some chaotic evolution, and we ended up with some time evolved state in some combined black hole and radiation system. This state, because of the chaotic evolution, resembles a thermal state, which looks like this.
Yes.
And now I'm just putting in this into that expression, the final expression that I derived last time.
Yes.
And that gives me a sum of over permutations, which has this structure.
So A and B are black hole and radiation.
Yeah, exactly. Yeah.
What can be thought of as justifying the state that they use, right?
Yeah.
Random position of them.
Yeah, you can see it at that level, or if you compare the entropies, then even if I'm not making any assumption about the structure of the state.
No, I'm not saying that you are making an assumption. I'm saying
Yeah.
that just starting from a very general, some very simple state size 0.
Yeah.
In the time evolution, you showed that this has to be entropy.
Yeah.
And as we discussed, this we can think of as something that comes from random states also,
Yeah.
right? And that's what they start with. So in that sense,
In
they're
that sense,
justifying
yes.
their choice of the state
Yeah.
as a natural state that would evolve as a time evolution.
Yeah. That's right. That's right.
But is it easy to see that somehow n should be a function of the amount of time that you travel the
So that is, that could be sort of put in by a hand here, that as you evolve in time, the size of these systems is changing. Yeah. So, what we use about the time evolution is the fact that it's chaotic, so that it even resembles a state like this.
So this could be just in the field theory, right? Could just be an
It's
S1
just in the field
coupled to-
theory. Yeah. So far, everything here is just in the field theory.
Right.
Does it have to be exactly this, or can it be like the radiation is at some finite temperature rather than infinite temperature?
You can also do the version where the radiation is in the finite temperature or at the same temperature. It's just for matching to their prescription, we would consider the infinite temperature case. Yeah.
So the additional factor about their case is that this kind of state has a nice photographic pose. That's the.
Yeah, but somehow if you assume that you're in JT gravity, then you can also start from this and say that, okay, now you have this Z and B is Euclidean path integral like this in the boundary theory, and because it's a holographic system, this should be equal to some bulk path integral. So actually here, from this perspective, it seems like the end of the world branes are not actually important, and this. So for instance, if I take this for Z4B, then this looks like some boundary path integral, which just has 4 copies, because I have 4 factors e to the minus beta h. And then, and then I just fill this in with some corresponding bulk geometry.
Sorry, but you will get a wrong answer. Right?
No, I think, no.
The right answer is the one that is given at the end of the book.
So to incorporate the end of the world branes into this picture, it seems like
Yeah, I really think you don't need endophthalmic. I'm sorry to
Yeah,
say.
yeah. No, it's,
Your setup doesn't require it, you know?
no, it doesn't.
Because what you're doing is actually more in the spirit of the Princeton paper, which frankly I find better. In that, all you're saying is, if I have some well-known configurations in the boundary theory, which I've argued should contribute, I'll just use ADS-CFT to do the corresponding.
Yeah, so now I just use
And you know-
ADS-CFT to actually calculate these individual factors.
Yeah.
Sorry, but how are you calculating that? That's the question. How are you calculating Z and B?
This,
So I just say that this is a boundary path integral. Because the system is holographic, it should be equal to a bulk path integral.
Okay, and what is the bulk path?
The bulk path integral is just the
What are the rules for the bulk path?
so it's just that now I'm using this temperature, which is 4 beta instead of beta.
Okay.
And in JT gravity, that just gives me some asymptotic boundary of length 4 beta. And then I can fill it in with this.
Just smoothly, you make it just as a disk. You want to fill it as a disk.
Yeah, you could, yeah, exactly. So in this case, the replica wormholes are not visible as these end of the world brains connecting the different copies.
But that will be different from what they have.
That will be different from their answer. So to match,
But should this not be exactly the same, because effectively the state that you are working with is the same?
yeah, I'm not sure if this. Yeah, I'm not sure exactly what role is played by the end of the world brain in the state that they're in.
And
Like,
at the end of the day, the island, the answer is the island formula. It only depends on the area of the horizon.
No, but let's talk about S10, right? And we can you go to 2 and go to 3 like that. There, those geometries that contributed were different from the distribution. Right? So, are you not getting a different answer if you propose this description of just filling it as a disk?
yeah, so let me tell you what modification of this will give. Like one thing you can do is just like directly compare the answer that you get. Like at the level of this equation, you can just compare the answer that you get here versus the answer that you get in their setup. And it seems like what you need to do is include some, in principle, I could have taken my equilibrium density matrix to be this, or to be this times some factor of the Hamiltonian, like some arbitrary function of the Hamiltonian.
Okay.
And then, you know, all of these would be modified so that instead of this, I have, inside this ZMB, I also have this f raised to the power of m. And if I make a particular choice of this function f of the energy, then that reproduces the end of the world brains.
I see. So you're
So like
saying
that
now
reproduces the answer for the end of the world brains. So that seems to be the only difference between this picture where you don't have end of the world brains, and here where you can imagine that you insert some factors of f, something like this. And now you say that, like in the analogous bulk picture, you should include some of the world brains. But somehow the fact that you have some different object connecting the different copies doesn't seem essential from our perspective.
let me just put it like this. I mean, my memory is not as great, but you know, the additional saddle points can be just seen in JT gravity root g r plus 5 times lambda with no extras end of the world. You know, the
From
fact
this
that-
perspective, yes.
No, not only just as a statement in gravity, you know, I can pose the question of computing various saddles with net deficit angle being what it is. And I get extra saddle points just in JT gravity. I mean, this was the spirit of the Princeton calculation. And then if, you know, they are there, you include them and see what their consequences are. And I think, I'm sorry, here all you're saying is, in JT gravity, compute the relevant, you know, path integral with these boundary conditions. So you're just going to translate, if I understand, your Zn1b to a calculation in JT gravity in the end. You know, which is actually, I think, if my memory serves me right, is the chain of argumentation in the Princeton paper. You know, you just directly do the calculations, seeing what you want
You
to do
mean
in the
this paper by
boundary.
Madasena?
Yeah.
Somehow, I actually understand that paper even less.
Okay, all right. But anyway, it's very much in the spirit of take the boundary calculation you want to do and do Lefkovich Maldacena /RT on it. Because once you know the boundary calculation, you can translate it.
Okay.
In that paper, what they coupling that if I thought they were taking a thermal field out of state,
Yeah.
and then coupling it to
And then coupling it to the
on the side.
on the two sides.
That's a different calculation which essentially doesn't have end of the world range, but it's because of the setup they consider.
Yeah, it doesn't have end because you can pose, as Samir showed, you can pose the information puzzle also for the thermofield double, letting both sides have happening. And that's a calculational convenience. But the theory they work with is JT gravity, no end of the branes world, and just do the path integral of JT gravity, which I understand. That's
I'm
all
saying
I'm
that
saying.
we don't get end of the world
Yeah.
range because of the particularities of the setup.
Yeah, that's true. I mean, Cher could do this for two radiation, two radiation fields coupled to two black holes in a thermofield dance.
Yeah,
She
that's
has a
not
general
what
setup, and then there will be a. Okay.
So if I try to reverse engineer from this particular state, that particular random state which will give you this, then the geometry that is dual to that state, you are saying, how does it look like? It will not have the end of the word brain state, without that F factor.
Yeah,
So
that's what it
without
seems
that
like,
effect-
because without this factor, you just calculate these partition functions in JT gravity at this temperature.
No, but what does the geometry look like as a dual of that state? How would that, the pictures that you do initially with the end of the world brains,
Yeah,
how would they change for the state that you have in mind?
for the state without F.
Yeah.
I think for that, we just look like I said before, like you just have,
No, I don't mean some sort of a trace road here, just a state.
oh, I see, like how do you see it as an overlap between states, etc.?
That you
I
won't see,
don't-
but you just
I don't know how to
compute
see
trace
that.
row to the end.
Like I don't know how to formulate an exactly analogous picture to theirs in terms of giving some prescription.
Is it like taking the intention of the brain to the
I'm
But
not.
then that is still a feature of that corner feature kind of.
I mean, the whole point of real Takamaki is you get the correct fine-grained entropy without knowing the states.
Yeah, right.
And, the spirit of the resolution is that you use Ryu Takamaki to get the page answer without knowing the fine.
Yeah, with the Takamaki is n going to 1. So I think n going to 1 is the end of the world with dwelling over.
Okay, but what I'm saying is you can do any n by mapping boundary you can do Lefkovich-Malasena n by n. No, it's not a question of calculational ease. It's a question of if I have to compute trace rho square in the boundary theory, I know what path integral is to be done conceptually in the path. Whether I can do it or not, I don't know, but I know what is to be done.
But that you have to take the input from the which state you are talking about, right?
No, I mean, yeah, okay, but if I know it's a thermal state, I want to do trace rho square, rho cube, I know how to do this in the, That's all I'm saying. Versions of this will take you home to the final new.
No, but I thought the states that they consider do have this end of the world plane.
Yeah, so there are two ways to look at it. I'm just saying, in my understanding, what's been achieved is to use the analog of Ryu Takamaki to compute the fine-grained entropy, without knowing the microscopic things. In 2D gravity, you have no actually string entropy. You don't really understand entropy. You need string entropy. Anyway, okay. Go on. But I see your point. I mean, your logic, I don't think it will work without end-of-the-world brains or whatever, as you are saying. It'll just work mapping this to GT, if I'm understanding it right.
Yeah, I think you can. Yeah, it depends on your there is a prescription you can give which maps to the end of the world brains, which is a factor, but I don't really see it from the boundary side the motivation for including that. I think your question. Sorry.
You agree, right? I mean, if this produces geometries without the end of the world plane, then there exists a question, a la BSSY, which also has this feature, right?
Yeah, let me.
They change the state a little without that f of h.
Yeah, it would. I think you're right. So I think now, because suppose, like, if I assume that I had a state like this, where, yeah, like, let's sum. something like this. Then the reduced density matrix of the radiation would again just look like this. So they would give you the overlaps of these states. And what we can do using this perspective is calculate these objects, the reduced density matrix, because this just is size 0, size 0. It's just this thing in our perspective. So now you can also apply the equilibrium approximation to a single matrix element using this U times U dagger thing, and then eventually the answer you get, keeping just this permutation part, is that. So yeah, so you have the normalization factor, and then you just have C1P times delta Ig. Sorry. Where now, yeah, so you're saying that this, if you assume that your state had this structure, then this overlap would be given by some Pathological which is like delta Ij times a single asymptotic copy of J gravity. Yeah, I guess it just gives you a circle. But then, then I don't know how to give a picture like theirs for calculating the entropy and entropy unless I start from this expression. Yeah. Anyway, so
Shreya, do I understand right that you're putting in that you know the size of the Hilbert space of this B part?
yeah,
A nice element about their computation is somehow it came out. Meaning they had naively even more states on the end of the world brain than the dimension of the Hilbert space, and then gravity told you that was impossible. That was a sort of cool thing, right? And here, because you could be doing the calculation here in the field theory, basically.
yeah.
And here, if I understand right, you're putting in the size of that. Right. Okay, thank you.
But somehow, even in their perspective, yeah, I'm not sure. I think the main, you could in principle write any combined state of the black hole and radiation in this form, right? With some.
Right, but they.
With some, and these states can't be orthogonal, just like whenever n is bigger than the dimension of p.
Right. Right, but let's say that gravity, we didn't know what the dimension of the Hilbert space of the inside was. And we thought we could perhaps make orthogonal states, and the two-point function, at the level of just computing two-point functions, they looked orthogonal.
Yeah.
And then the gravity path integral tells us that that's impossible.
Yeah. But somehow, yeah, but that involves putting in rules
so
which
S
I'm
naught
not sure.
enters there.
S naught enters there in the sense that
Some higher topology.
exactly, it's basically that you could connect this way with this way.
Yeah.
Yep.
Two boundaries.
Yeah. So suppose I was trying to compute the expectation value of a product of two of these overlaps. I with j with I with j. If it was exactly orthogonal, you get 0. But now you can connect this I with this I and this j with this j. So you get something non-zero but very small.
There's a trade-off between two boundary depth higher topology versus something.
Yeah, at the level of just the inner product, it's just a very small matrix element. But you then see the size of the Hilbert space from this entangled in entropy combination. That you just cannot entangle more than each the pi, it's not states.
Yeah.
I was wondering if that element, it's probably a stupid question. But
No, I think it's a good question, but somehow, the rules that they put in, because I don't understand the source of the rules, I'm not sure if it's not somehow implicitly assumed in their rules that that these states are not orthogonal. But
I mean, okay, not that I know the story very well, but it is assumed if you assume that this size of the Hilbert space was e to the pi, it's not. But that wasn't put in, it came out. I thought that was a cool thing about it.
Here, what's being put in by hand is the size of the radiation, right? This n, capital N.
Thanks.
And as the capital N becomes larger and larger, in Shreya's model, you can take n to be as large.
Yes,
And
but
then she sees this in the face.
But with the boundary Hilbert space is fixed.
Yeah, here I'm
dimension, which she
assuming the
knows.
unitarity of the boundary.
And that's where it comes from.
Yes.
Whereas in the gravity calculation, even the path integral told you that the boundary Hilbert
But it
space
was a
is.
very similar thing, right? You want the radiation size to be larger and larger. And then at some point it crossed the size of the bunch.
It crosses, but the gravity calculation tells you what the size of that
Yeah.
boundary Hilbert
Yeah,
space
yeah,
is.
yeah.
You didn't have to put it in.
Yeah.
Yeah,
Well,
yeah.
that's true. I see your point, but I think here what she's saying is, look, she's going to motivate this to do a gravity calculation. Okay. Because ultimately it's a gravity calculation.
Yeah, so here I'm assuming the unitarity, I'm assuming the size of the dimension, I'm just trying to figure out what gravity calculation
Yeah.
gives me the unitary part of the result, and from that I find that it's right.
And the non-trivial check is that gravity should have that contribution.
Yeah.
Right?
Yeah, I understand.
In particular, even in this calculation, I think Shreya would say that the size of the black hole is given by the gravity.
But this formula is justified by
Yeah,
knowing.
because I calculate these path integrals
Yes.
using the gravity side.
Yes, exactly.
Yeah,
Wait. Oh, I see. You calculate those path integrals using gravity. I see.
Yeah, so it's a completely I mean,
I
it's motivated as if gravity was a standard system of the type you talked about, but eventually the calculations.
I see.
And then it tests whether gravity is.
So you're not explicitly putting in your knowledge of the dimension of the Hilbert space into your calculation. That's just coming out of
Yeah.
what gravity is. Okay, thank you.
It's really only and.
Okay, thank you.
yeah, but it shows more why you should include these connected.
I see. Thank you.
Okay, so I think since it's close to lunchtime, what time do you think I should wrap up?
Whatever is a good time for you.
Yeah, I'm wondering if I should say,
There was one small thing you said in your beginning introduction, which is they hadn't done it quite right because there was some state they didn't get right. Was something like that.
yeah, somehow I think part of what I'm not sure, it's not that they didn't get the state right, I just didn't understand why, like, this psi I, psi j in their picture should have been calculated using this Euclidean path integral, because I just don't see, like, how, yeah, somehow I don't see what this picture has to do with Hawking's geometry. Yeah, but that was kind of a vague statement. Yeah. Okay, so one final thing that I mentioned about this is, it's related to calculating this matrix element. So, in PSSY, we point out that there's something strange about these replica wormholes, which is that it seems to suggest that this quantity, rho ij absolute value squared, doesn't seem to factorize into rho ij shell, according to their calculation. And the reason for this was that if you calculate the rho ij, then you a single rho ij, then that doesn't know anything about the replica wormhole contribution, whereas if you calculate something with two copies, then it does know about the replica wormholes. So let me just, there is a similar apparent paradox in our context, which is that if you apply the equilibrium approximation to this rho rij, then recall that there was some diagonal path which we kept, like some path associated with permutations which we kept. And then some time-dependent path which was supposed to include the fluctuations around equilibrium, which we threw out. But then when you calculate Z2 of R, which is a sum over Ij of these matrix elements, then it seems, so this contribution, just which we kept, just looked like 1 over n delta Ij. Okay. But this, according to our calculation, looks like 1 over n plus 1 over e to the s0 times some order 1 thing. So at times after the page time, this should be the dominant contribution, but this seems to be missing based on the approximation of the individual matrix elements. Okay, and the resolution of this apparent paradox is that even though these individual deltas are small, when you add up these many of them, there are many, like order n squared of them which contribute. and so they can add up together to produce this contribution. So, so the resolution in our perspective is coming from the fact that there are some fluctuations around equilibrium of this quantity. And so this is kind of different from the perspective which was suggested in PSSY, which was that somehow instead of a single theory, you should think of the boundary theory as an ensemble average, and fluctuations like this would come from fluctuations around the ensemble average. So from this perspective, you don't need the ensemble average, and it just has to do with fluctuations around equilibrium. Coming from.
So this delta is defined by what in your?
So yeah, so delta is defined by. So you remember last time we wrote this expression where we projected onto the permutation pipe, and then we left out everything else. And I called that Q last time. So that is this is the Q for this one. Okay, so that was just something I wanted to mention about another way in which this can be seen as clarifying some aspects of PSSY. Okay, yeah, so I'm going to stop there, and I'm wondering if, yeah, like for the next part, somehow it's kind of a completely different perspective, so I don't know if it's better to stop now and start next time, or to just introduce that and. I don't know.
If the audience, unfortunately, there's a meeting I have to go to and I might not be able to attend your talk tomorrow.
Okay.
So is there, if you will all permit, if there's a 5-minute, like, broad brush picture of what you'd say,
Yeah.
Can that be permitted?
Would it be, like, the time we have to talk on Friday? Some other time, like, we share the time.
Oh, if you could do it on Friday. Yeah, but I don't want to inconvenience you, I'm sorry.
No, I mean, if it's okay with everybody, good, then, I mean, it'd be great if you. Yeah.
Yes, does Friday not work for anyone?
So, I do it on.
Yeah, I'm around on Friday. Okay, I don't want to do this, but
After.
sorry, this meeting just got done.
Do you still wanna like start the?
Yeah, maybe it would be good to start because I feel like it'll be hard to get through anyway. So,
Do you need a license?
yeah.
Thank you. Should I give you?
Uh,
You're good and
Yeah.
talk.
Are you still connecting to the internet? Yeah, should I just start? Okay. So,
Beginning of teaching.
yeah. Yeah. Okay. Okay, yeah. So I'll now switch perspectives a little bit to talking about this paper with Chris Netter, Daniel, and Jeff. Yeah, so this perspective will involve viewing area CFT as a map between Hilbert spaces. So far, we derived theoretical wormholes by using a physical input on the boundary side of area CFT, and then combining it with some known entry of the dictionary, which is just the equality between bulk and boundary path integrals. But more recently, area CFT has been understood as a map between Hilbert spaces. So on the left-hand side, you have the Hilbert space of the low-energy excitations of quantum fields on some fixed classical geometry. So this is what I've been calling the effective picture, and it'll have some Hilbert space, which I'll call H effective. And then on the CFT side, can be seen as the full fundamental description of the system. So its Hilbert space will be called H fundamental. People have made a lot of explicit models for what this map should look like, in some cases in terms of random heads and networks, which have been very useful for understanding what properties of this map give rise to various entries of the dictionary. And in particular, it's been understood how something like the QES formula arises from properties of this map. But somehow these existing models were all for cases where this H effective didn't include the black hole interior. So either there was no black hole in the classical geometry, or if there was a black hole, then you just consider somehow the part of the geometry outside the black hole.
So I'm really sorry, I should wait and I should have known this, but these are essentially what discretizations of the bulk. I mean, because you're saying they don't include or include the black hole. So these are some, is that what it is? I mean, okay, anyway.
Yeah, I guess you,
tell us a bit.
when you make your effective Hilbert space, then that involves some assumption about, so yeah, I'm defining the effective Hilbert space as fixing your bulk geometry, and then considering all possible excitations of the matter fields on that.
Okay.
So then in this, you can either choose to have geometries with black holes or not have geometries with black holes. But now, motivated by the fact that something like the QES formula does work even for the evaporating black hole setup, we try to make the simplest possible model for the bulk to boundary map, which is consistent with the island formula. Okay, so the key thing that's different about the case with and without the black hole is that in cases without the black holes, the effective Hilbert space dimension is smaller than the fundamental Hilbert space dimension, because you're restricting to low energies and there isn't like a region with a very large volume. So this map from the bulk to the boundary is an isometry, which means that v dagger v is equal to the identity on the input Hilbert space, and this means that it preserves inner products between the effective dimension states and the output states. And in fact, this turns out to be a very special kind of isometry, which has certain so-called error correction properties, which we'll talk about if we have time. But in cases with a black hole, the dimension of the effective Hilbert space looks like it's exponential in the volume of the black hole interior, whereas the dimension of the fundamental Hilbert space is exponential in the black hole entropy, which is the area of the horizon over 4G. So at sufficiently late times, the effective Hilbert space dimension is much bigger than the fundamental Hilbert space dimension. And in this case, there is no way that the map can be an isometry. Okay, so it has to have some surprising features, like there should be a lot of bulk states which have norm 1 on the bulk side, but they map to states of norm, they just map to 0 on the boundary side. So they don't really exist in the fundamental description.
As we've just seen in your PSSY calculation.
Yeah, it's exactly. Like, for instance, the PSSY calculation, you can see that you assume that maybe the bulk states, psi, small I, were all orthonormal, but you find that they can't be orthonormal. So that is also a feature of a non-isometric map. So we want to use what we've learned.
But I mean, just to put it to the observer inside, seeing that these bags of gold in this large volume or whatever, they look pretty close to orthogonal.
Yeah.
So part of the satisfactory resolution should be to explain how that happens, right? If you're actually going to, I'm just saying, like, if we really want to explain the conflict with the sense of locality we have,
Yeah.
we should be able to say why. It's small non-orthogonality which builds up, is that's somehow the point. But locally, as you're going along inside, it seems you're.
Yeah, it seems like there's nothing wrong with
Yeah.
this geometry. Yeah, that's
This
part of
will-
the
this
question
will
we try to
help.
address. Yeah. Yeah, so now we want to use what we've learned from these holographic models so far to make the simplest possible model for this non-isometric beam. Okay, so let's just remind ourselves of what the holographic setup looked like for the evaporating black hole. So the black hole was a holographic system and it maps to some non-gravitational system in a lower dimension. And in this, I've included some right-moving modes, which are partners of the Hawking radiation, which are labeled small r, and then some left-going modes, which can be seen as whatever matter went in to form the black hole. But the size of the interior is increasing because of an increasing number of these r modes. Yeah, so in a single space-like slice, which you can choose to be some nice slice, which has some low curvature and low energy density everywhere in the bulk, seems like we map this Hilbert space to a Hilbert space of some other system, small capital B, yeah, and then nothing happens to the radiation in this setup. So the map on the radiation is just the identity. Okay, so the map has this kind of structure. And as we just said, B is not an isometry application. So while we don't know a lot of things about this map, like we don't know, given a certain state rho in the bulk, what the state sigma is, if we assume that the QES formula is correct with islands, then given any state rho, we can we know what the entropies of sigma should be. Okay? And in particular, if you take a bulk state, which appears in Hawking's calculation, where you can take the left moving modes to just be some pure state, and the right moving modes are in some increasingly entangled state between small r and capital R. Then we know using the QES formula that the entropies of sigma will obey the page rule. Okay, and in principle, we can use the QES formula for any other input state as well.
Sure, just to be sure, I thought the whole point of the island was that the degrees inside the island could not be reconstructed on the boundary, right? They would be reconstructed, at least you would need the radiation to reconstruct them.
Yes.
Right? So, I mean, you won't try to, I presume, map those degrees of freedom inside the island onto the boundary alone, right? Isn't it?
You mean the map shouldn't have this kind of factorized structure?
Yeah, I mean, I was thinking it's okay for the region between the boundary of JT or ADS and where the island begins to try and reconstruct those degrees on the boundary. But for the degrees inside the island, you would at the very least need the radiation. I'm not sure that's
but
enough.
somehow this is not in contradiction with that.
Okay, but
Also-
the tensor product identity, so I'm just wondering how that's going
Yeah.
to work out.
Yeah, I guess maybe just to, so somehow all of that will come from the fact that B is not an isometry. And one intuition for why, I guess, so mostly we have intuition from the case where B is an isometry. And one thing that would imply is that, the reduced density matrix of rho, it would seem that, we're getting a different result in the setup for the entropy of rho in R versus the entropy of sigma in R. Because the entropy of rho in R is just always given by log R in the Hawking state. But
What
for
is sigma, including the island?
so sigma, so here this map takes as an input rho, and its output, whatever this map is, its output is sigma.
Output is a map. What is the out? I mean, this is in.
Sorry, I'm just saying that sigma BR is the state that's obtained by acting with B.
Okay.
on
I
this
see.
state.
So the identity was to say that that little r was the same as big R?
Yeah. No.
What was that?
No.
Please explain that identity factor.
The identity factor. So, okay. So here the input is
Oh, radiation, that's the radiation.
radiation. Yeah. The capital R maps to capital R. Like nothing happens.
I see. So you will keep the radiation the way it is, but by the manner in which the left and right regions inside will map to B, you will accomplish.
Yeah, it looks like they're mapping to B based on how we've written it.
Yeah. Or if that's not true, then
But
okay.
yeah, but some intuition for why. Like
Okay.
why our usual reasoning about the isometric case doesn't apply in the non-isometric case is that from the structure of this map, you would have thought that like if V was an isometry, you expect that the this map should not be able to change the entropy of the reduced state on R. Like you would expect that these two quantities are equal, right? Because you'd say like, oh, this map is not even acting on R. But actually we find instead that like we want to find that the entropy of R is just increasing. The entropy of rho R is always increasing, whereas the entropy of sigma R is given by the page curve. And somehow that can happen in cases where B is not an isometry.
Even though it's in tensor with identity.
Yeah. And in a similar way, in a similar way, this V will also be able to send information from the from this LR into capital R. But the reconstruction is a bit even more counterintuitive in this setting. So it's something called state-specific reconstruction, which I'll try to explain. But it doesn't work in the usual way as it does for isometries.
Can I place some R on both sides? The capital R on both sides of this equation?
In this state, then that gives you sigma B and
That V is approximate isometry still.
V is not an approximate isometry.
The new V. After trace out R, you get some V that acts on rho LR that gives you sigma B.
Yeah. But if you trace out R, then you have a map from. Sorry, you mean instead of this, I should write this thing?
Yeah, both sides.
Okay. But then I don't. You mean just ignore R in the setup?
Trace R is straight.
Okay.
So then you get some black hole density matrix and LR density matrix, and you get some sort of an approximate isometry.
No, it still can't be an isometry because LR is much bigger than V.
Is it the same type of non-isometry that you're talking about, or
Yeah.
can we capture using just this, or do you need this factor of R also?
Oh, I don't need the factor of R. Like I could have just talked about it as a map from LR to B.
Okay.
But I included this R to make to check that I'm getting the QES formula. But I could have just not attached anything to the system, and I would still have an issue with it being an isometry.
So Shreya, can I just re-ask Sandeep's question?
Yeah.
Wouldn't you? I thought as Sandeep was saying that you expect after page time for there to be a map from LR to R and not to B.
Yeah.
Why? Sorry, you said something I could understand. Why is that consistent with what you're doing? I mean, aren't these states encoded for in the Hilbert space of R, not in the Hilbert space?
Yeah, somehow the encoding will work differently in this case, and you will only have an encoding of operators, which like you'll only be able to say that some bulk operator is reconstructed in some boundary region for a particular state.
Okay.
And then if you allow states which are entangled between the interior and the exterior, then that combined with a non-isometric V can somehow project the information from the interior into the.
If I perform a unitary on R, can I change what's happening inside by performing a very complicated unitary on R or a very complicated unitary on B? Can I create a truck inside the black hole by performing a very complicated unitary on R or on B?
It should be on R.
R.
Yeah.
And this doesn't contradict what you said.
This, yeah, because it will actually be only for a particular state and not for the entire Hilbert space. And so somehow, like a particular input state which is entangled between R and R, combined with this not being an isometry, can somehow take the information from here and put it in here.
Right, but I'm not talking about information, but talking about changing things.
Changing things.
I change something in R, does that change what happens inside the black hole?
Yeah, I guess my interpretation of that is what is the bulk operator that's due to this boundary operation that you're doing? And is it in R or is it in the black hole?
Yeah, but I'd like to ask it physically. I want to create a truck in the center of the black hole. Some very complicated unitary operator will do that trick creation. It acts either on B or on R or on both.
Yeah.
The expectation is that it acts on R.
At least must act on it.
Yeah, and
Yeah.
Primarily
it
acts.
will not be able to do it by just acting.
Yes.
Yeah,
You
I
cannot
agree
do
with
it
that
by-
statement,
yeah.
and it can be consistent with this.
It can be consistent.
Because instead of asking that question, somehow you'll be asking, can I construct a truck in the black hole if the bulk state is the Hawking state? So somehow the question is phrased a little bit differently.
But the isometry is only from LR to B, right? You cannot do anything on R dynamics that changes state inside a black hole.
That was the point. Yeah.
No, this B, LR to B is a map from LR to B. It's not at all acting on R. So,
Yeah.
I mean, even if it's not an isometry, any action on R cannot change anything inside a black hole.
Maybe the point is that L is part of the island, let's say,
Yeah.
or whatever. Some part of this LR is so entangled with capital R that if you know the state, then instead of acting with the operator on R to create the truck, do something. I don't know if that's what's going on. Some state dependent sometimes can be.
Yes, that's my model. We just think of this as think of this V as something which maps the states of the end of the world right into the psi i's.
Yeah.
Like that's what it is.
Yeah.
It's clear that
Oh,
that's a
I
map from.
That's-
Bulk space above.
Yeah.
I say it's
Yeah, I was just giving an example. So in the PSSY model, there are the states of the end of the world range.
Yes.
You can think of the LR of the space.
yeah.
And then there are the states psi I, which are the black hole states. That's V, right? The map
From the end of the
Psi I are on the boundary.
one in V.
Okay. So this is some association.
Yeah, looking at it.
It's not really
It's not an isometry.
it's not the statement that these are these things. It's just some bigger association.
But even then, you would be able to create Shiraz's truck by just acting on B, right? Because,
can't. The PSSY calculation shows that we can't.
but, okay, then I still have my, I mean, okay, there
This
is
is the fact that this V is not an isometry. It looks like an isometry long before page-time, but after page-time, it's really apparently non-isometry. This is something.
Yeah, it's definitely not, yeah.
Yeah.
That is a good point.
But this I of R, the identity of R, still bothers me, even with all this, right? Because there has to be some information about the track in the radiation.
Yeah.
I of R seems to say that nothing has been done to the radiation.
Yeah, so somehow, and someone asked me the point that, even if B is not an isometry, how can it map things from LR to R? But somehow this is because the reconstruction happens in a state-dependent way. And, yeah,
There is
I'll try to
a lot of
explain this.
entanglement effectively between LR and R.
Yeah, exactly.
Right.
Presume that there is a lot of entanglement between LR and R on this side, and somehow that allows, and that and the fact that this is not an isometry, the state is not an isometry, sorry, this map is not an isometry, will allow reconstruction of operators in the radiation. Yeah, and the intuition for that really is like, from this perspective, like the input state, like if you take the input state to be this Hawking state, then it seems like rho r is just maximally mixed, so it doesn't contain any information. But sigma r that you get as an output of this, if V is not an isometry, is not a maximally mixed state, so it does have some information.
So, I mean, the rho of R had entropy because the radiation was entangled with stuff inside.
Yeah.
And you messed up the stuff inside in a sort of non-isometry way to change that amount of entanglement.
Yeah,
Right?
yeah.
Somehow, even then, the identity is confused. But okay, yeah.
I'm sorry, Shay, I'll just ask one more time.
Yeah.
The state with the truck and the state without the truck, do they map to exactly the same radiation state?
State with the truck and
Yes.
Who can, right?
But it looked like that. It looks like that from here, right? Because that's a map from LR, which is with or without the truck, to B, and the
Yeah.
identity on R.
I mean, that's not.
No,
supposed
no, just the identity on R doesn't tell you that rho R is equal to sigma R, as you can see from calculating the entropies.
What?
Yeah, so it's easier
So-
for us to see how the entropy would change, but how would.
But if the entropy is different, then clearly these densities are different.
I see. You're saying that the map was from LR and R to B and R. So obviously R maps to R. There's no content in that because R is R.
Yeah. I mean, you can also just see from how these holographic calculations are done that
Right.
the radiation is just not a holographic system. It's
Right.
exactly the same. Like,
I think I.
yeah. Yeah, but somehow you can still, even though you're acting with the identity on R, if your input state is an entangled state between LR and R,
Yeah.
then you can change the reduced density matrix not just on, sorry? Yeah. You can change the reduced density matrix not just on from LR to B, but also on R.
It seems to me that the fact that its identity on R has no content. I mean, it's obvious because you're just saying the radiation state is the radiation state, right? So
Yeah.
No, but usually we prove the fact that the bulk is reconstructed in the radiation by changing the radiation
yeah,
and saying it changes the bulk, right?
The state on the radiation
And-
changes.
yeah.
And
So
what Shreya is saying is that even though the reconstruction acts only, even though the island will be, I mean, the island is, it's not right to say that the island is reconstructed on the boundary of the bulk in any way, right? That VLR to B sort of misleads one somehow. I got
It's
to sort it
not,
out.
it's no, at this stage, so I'm not thinking about operator reconstruction yet. I'm just saying I have some input input
State-
space and some
state.
output input space. And I'm writing down the structure of the map between them. And yeah, so nothing, yeah. And I'm not doing anything non-trivial on the radiation system in this map.
but is the domain of this map smaller than you might expect? The fact that you cannot independently, you're mapping from a state on LR plus radiation to something. But now, if radiation reconstructs the state on LR, then you should not be able to independently vary the states on LR and the radiation state. So there should be some connection. So the domain of your map should have this thing put in. Is that wrong? That you should not be able to independently vary what's happening here and on the radiation.
Yeah, somehow like I think the point of doing this is to be able to separate statements that we make on the bulk side and the effective description and the fundamental description.
Okay.
So here we really do want to consider all possible input states in the fundamental description. But of course, they should, like the true number of states is the number of states in the fundamental description. So part of the question would be like, yeah, but I don't know if we should talk about like doing something in the fundamental, like, I don't know if we should use a statement about which operators get reconstructed where in the fundamental description to say that something, that you should restrict the set of states in the effective description.
Yeah, so truck and particular radiation state is an allowed input to your map, and no truck and the same radiation state is also an allowed
Yeah.
input. Sounds strange, right?
Yeah, it is strange. Yeah, but I think hopefully that once we have a model for the setup, then we'll be able to clarify it.
Sorry. Yeah.
Okay.
She said that.
Sorry, I really have to go.
Yeah.
Maybe that's it.
That's all we.
Maybe that's it.
Sorry, what?
Sorry, say it again.
some of these states map to zero, right? So,
Yeah, some of the states map to 0. So exactly, so maybe
The states that are illegal will map to
the
zero.
states that are illegal will map to 0. But in principle, at this stage, I just want to consider, I want to see what happens to this Hilbert space. I want to include everything in it, right?
Fine.
Okay. Yeah. So our requirement on this map will just be that it should turn out to be consistent with the QES formula. Okay. And the simplest map that we can make, which has all of these features.
Sorry, could I? Onkar, rather than have Shreya rush through it, we could even have a fourth lecture or something. Right?
Yeah, sure.
She's here next week as well.
Yeah.
So my suggestion is that when you find a
Okay. Should I just? We could. Should I
whenever
just
you feel
introduce?
this, yeah.
I only have 2 more slides in this actually
Okay,
for the
great.
intro part.
Yeah.
So
Next week I'm not here, but anyway, go ahead.
yeah, I think I should be able to cover. If I get through this intro part, maybe I can cover a lot of stuff. Okay. Yeah. So. Yeah. Okay. So the simplest model that we can make after the page time when LR is bigger than B is just that you take LR, you have some unitary which acts on LR, but the dimension of the output B should be smaller than the dimension of the input. So you just add some system P to make the dimensions the same, and then project onto some arbitrary state, which we can call 0 in P. Okay? And then this factor is essentially included to make the average normalization the same between the 2 sides, but it's just some overall factor. Okay, and here we assume that this unitary U is some typical unitary matrix from the Haar ensemble. So the reason for doing this is that just that we expect that the bug-to-boundary map should be complicated, and this is a simple way of considering a complicated map, but we don't use ensemble averaging intrinsically, and the map is not defined through an ensemble average, it's just defined for some specific realization of a typical unitary. Okay, and now given this map, one thing that we can check immediately is that we can just find what it gives for any input row. We can find what it gives for the entropies of sigma. Okay, because rho would just be the input, and then you can do some average over U's to find the any entropy of sigma B and sigma R in the output. Okay, and I won't explain the details of how to do this calculation, but it'll turn out that the entropies are exactly consistent with the QES formula for any input state. And in particular, it'll include an island contribution, etc. Okay, and yeah, so then this is the simplest model that we could have made, which is consistent with the QES formula. And now that we have this model, we can try to address the kinds of questions that we've already been asking. Okay, so the first question that I'll try to address, I don't know if, okay, let me just summarize it. So this is already the type of thing we were talking about, that in our usual understanding, QFT on some fixed background should be a good approximation to quantum gravity if the curvature is small everywhere and the energy density is low everywhere. And it seems like for the evaporating black hole setup, if you consider a nice slice, even after the page time, both of these conditions are still satisfied. But since B is non-isometric, it seems to annihilate many of these states in the effective Hilbert space, telling you that they don't exist in the fundamental description. So we want to find what feature of these bulk states is making them unphysical if they are consistent with both of these conditions. So to try to answer this question, what we do is that in this random unitary model that I showed in the previous slide, we show that the inner products of all states whose complexity is less than exponential in the black hole entropy will be preserved by the holographic map. So in particular, their norms are preserved and they don't get mapped to 0. And so this suggests that maybe the additional restriction that you should add to this list is that the complexity of the input state is small. So I'll go through the details of that calculation in the next lecture.
So any urgent questions before don't be afraid. All right, okay, so if not, we'll reconvene on Friday, not tomorrow, on Friday. And we'll try to send out an email announcement to the Times. decide. So that's fine, Shreya. Yeah.